Alright, so let's do another example of U substitution. We'll be doing plenty of these. So integral of sine of 7 theta plus 5 and then d theta. Okay, so if we want to find this integral, first of all, using U substitution, we see that we have an outer function and an inside function, right? So we do have to use U substitution here. So first of all, the first step is to choose our U. So what I'm going to make U is whatever we see inside that set of parentheses, right? So U is going to be equal 7 theta plus 5. Okay, the second step is to find our du. So if we differentiate implicitly, we get 7 d theta. Okay, so that's what we have here. That 5 just goes away, right? So now we want to get d theta by itself. So in order to do so, we're going to divide by 7 on both sides. So we get that d theta is equal to du over 7. Okay, so now that we have this piece of information, as well as this one up here, we're going to replace everything that we see in our original integral, everything that we can replace, that is, with u things. Okay, so we're going to have sine of, instead of 7 theta plus 5, we can replace that with a u, and now d theta is replaced by a du over 7. Okay, so now what we can do is actually bring this 1 over 7 outside, because that's just a constant, right? So we have 1 over 7 times the integral of sine u du, and now we're just going to integrate like normal, right? So now we get 1 over 7 times negative cosine u, and then plus a c. Can't forget that c there because we're doing an indefinite integral, right? And then our last step is just to replace that u with things in our original variable, which was theta. So we're going to replace that with, so we have a negative 1 over 7, and then cosine of u, which is now, we're back to our 7 theta plus 5. And then we have, of course, our plus c at the end. Okay, so now that we have learned the U substitution method for indefinite integrals, we're going to do it for, now we're going to do it for definite integrals. Definite meaning that we do have limits of integration. So for definite integrals, okay, so basically we're going to go through the same exact process, okay, and then once we get to the final integration, instead of writing a plus c, we're going to evaluate what we get, our antiderivative, once we have that, at our endpoints or our limits of integration a and b. So there are actually two ways to go about this, though, evaluating our function or our interval. So the first way is to go through U substitution, okay, and then so go through U substitution. We're going to do that, and then at the end we replace U with x terms. At the end. Okay? So if we do that, then we're going to I'll actually say we're going to evaluate our antiderivative in terms of x with, or evaluate at the original x limits of integration. X limits of, and I'll just write the integral symbol of integration, okay? So that's the first method. We're just going to go all the way through, replace our u with x's at the end, and then use those original x limits. The other way we could do it is to go through U substitution, okay? And then at the end, we're going to not replace u with x stuff, but we're going to keep everything in terms of u. And when we do that, then that means we're going to have to use and then evaluate at new u limits of integration. Okay, and this process here, this second method is called change of variables, because we're actually changing everything into u at the end and solving for it that way. So change of variables. Hold on here. There we go. Okay, so change of variables. I was trying to squeeze an S in there. All right, so let's see an example of both of these for definite integrals. So let's solve the problem, the integral from 0 to 2 of x squared times the square root of x to the third plus 1, and then we have a dx. Okay, so the first method that we're going to do is with our original x limits. We're going to replace everything with x's at the end. Okay, so number one, we're going to basically just solve for U substitution. So first of all, what we have to do is pick a U. So U, in my opinion, should be everything that we see inside the square root. So this will be an x to the third plus 1. Okay, and now what we want to do is find our du. So du is going to be equal to 3x squared, and dx. So now what we want to get is dx by itself, so then we divide by that 3x squared on both sides, okay? And then those cancel out, and we get that dx is then equal to du over 3x squared. Okay, so now that we have this, we can replace things with u terms. Okay, so when we do this, technically, because here we started with limits of integration, but when we switch into u's, we either have to switch those limits of integration to be in terms of u, or just what I do, if I know I'm going to be switching back into x's anyways at the end, what I do when I switch into u's is I just kind of ignore those limits right there, and I turn it into an indefinite integral for the time being. So it's kind of just blank, okay? So instead of that, I'm just not going to write the 0 or 2 at all, and then I'm going to keep going with the u substitution. So for x squared, we don't have anything to replace that exactly, so I'm just going to leave it there. And then we have x, the square root of x to the third plus 1, that is now replaced with a u. And then we have our dx, which is replaced with a du over 3x squared. So du over 3x squared. Okay, so this is where we're at, and we see that our x squareds can cancel on top and bottom conveniently, right? And we have this factor of 1 over 3, which I can move to the front. So we have a 1 over 3 times the integral of u to the 1/2 power, right? That's the square root of u, okay? So at this point, I'm just going to integrate like normal. So this will be 1 over 3, and then times u to the 3/2 if we add a 1 to that power, and then we have to put the reciprocal in the front, okay? And then we're not going to have this plus c because it's technically not an indefinite integral. I'm just ignoring the bounds for now, okay? So I'm going to leave it like this, and then what we're going to do, so after that, I'll just combine this. So this is 2 over 9 u to the 3/2. Okay, so keep this in mind. This is the step that we're at, and I'll continue this on the next slide. Okay, so here's where we're at. We're at 2 over 9, and then times u to the 3/2 power. So here is where I'm going to reimplement, or reinstall. We're going to replace. Okay, we're going to replace with x stuff. Okay, and when we do replace with x stuff, so 2 over 9, and in for u, we're replacing what we subbed out, so that would be x to the third plus 1, and then to the 3/2, and when we replace it with x stuff, that also includes the bounds as well, the limits, so that'd be from 0 to 2, okay? So we can kind of think of this that the limits were kind of on a vacation for a while when we were in u territory, okay? So anyways, so now we're just going to solve through. We're going to evaluate this antiderivative at 2, and then minus the antiderivative at 0, okay? So this is going to turn out to be a 2 over 9 times 2 to the third plus 1 to the 3/2 power, and then minus a 2 over 9 times 0 to the third plus 1 to the 3/2 power. And this is going to turn out to be, so inside here we have, so this is a 2 over 9 times a 9 to the 3/2 power, minus the 2 over 9 times 1, basically. And then this is going to give us, so 2 over 9 times 2 over 9 times square root of 9 is a 3, and to the third power is a 27. And then we have minus this 2 over 9. So this is basically going to give us a 54, that is 54 over 9 minus a 2 over 9. So this will give us a positive 52 over 9 as our answer, okay? So that's pretty much it. We just went through u as kind of like a pathway or a bridge, and that was basically it. And like I said, our bounds or our limits took a break. They went on vacation during that time that we were in the u land, the land of u. Okay, so that was the first method, and we got an answer of 52 over 9. So now let's do it the second method. So method 2, also called change of variables. Change of variables. So again, I'll write the problem down. So we have the integral from 0 to 2 of x squared, and then square root of x to the third plus 1 dx. Okay, so if we do it this way, we're going to do the same exact process, except for at the end it changes a little bit, okay? So again, we're going to pick our u to be x to the third plus 1, okay? And then so therefore our du is equal to 3x squared dx, and so dx is consequently du over 3x squared, okay? So now we're going to replace that in here. We're going to place everything in here with u's where we can, okay? All right, so now we have the integral of x squared, and then this square root in here, instead of that being x to the third plus 1, we can replace that with a u. Okay, and dx again is replaced with du over 3x squared. Okay, but here's the difference. Here's where it comes in. So instead of leaving these limits blank, okay, instead of leaving this as like an indefinite integral sort of, what we're going to do instead, because now we know for the second method, we're going to change completely into the land of u. All right, so we're going to keep everything in u, keep in terms of u, even at the end, in terms of u. So that means we're never going back into x territory. So that means we have to change these bounds, okay, to be in terms of u. So how do we do that? We're going to make use of our equation that we chosen for u, okay? So that means u is equal to x to the third plus 1. So what we're going to do is take this bottom limit and the top limit and figure out what they mean, or how they're written in terms of u, okay? Alright, so for the bottom limit, this is going to be u of 0 is equal to 0 to the third plus 1, so that's equal to 1. So that means our bottom limit here, in terms of u, that's written as a 1, okay? And then for the top limit, we're going to plug in a 2 there into our u formula, so it'll be 2 to the third plus 1, so that's equal to 8 plus 1, which is a 9, okay? So this is going to be the upper limit, our new upper limit. So now we have this, and we're going to continue on. Alright, so now we have integral from 1 to 9. These are our new u bounds, or our new u limits, okay? And then we had this x squared, and then times the square root of u, and then du over a 3x squared, okay? So we can cancel out those x squareds conveniently. We'll move this 1 over 3 to the front, so this is going to be 1 over 3, as the integral goes from 1 to 9, of the square root of u, also known as u to the 1/2 power, du. Okay? So now that we're here, we can continue integrating like normal. So we have a normal single variable integration going on. So this is going to be u to the 3 over 2 when we add 1 to the power. We're going to multiply by the reciprocal in front, and we're going to evaluate this from 1 to 9, as u goes from 1 to 9, okay? So this is going to be 2 over 9, u to the 3/2 power, and then 1 to 9, okay? So then when we evaluate this, we get 2 over 9 times 9 to the 3/2 minus 2 over 9 times 1 to the 3/2. This is going to turn out to be 2 over 9 times a 27, okay? So 2 over 9 times 27 minus a 2 over 9, which is our 54 over 9 minus 2 over 9, which is equal to a 52 over 9. Okay, so we get the same answer. This was the second method where at the end, we didn't switch back into x's, but we just stayed in u. Therefore, that was a complete change of variables. Alright, so that wraps it up for this concepts video on the substitution method. I hope that helps, and good luck on your homework.